Hi, my name is Maggie Monahan, and this is my video lab report for Physics 2212, Lab 2. The purpose of this lab is to find a more accurate electric charge of 1U tape by treating it as a line of charges rather than just treating the tape as one point particle, as was done in Lab 1. In this lab, we will expand upon results found in Lab 1 using the same system of two charged tapes with one suspended above the other. We will also use Python in order to visualize and compute more complex systems and electric fields. Some major concepts for this lab are Coulomb's law, electric force, the idea of a distributed charge, and Newton's second law. In this experiment, two tapes were charged and its interactions with other objects, such as a hand, another charged tape, and a pen were observed. To do this, tape A and tape B were charged by pulling them off of the base tape. Then, tape B was suspended and tape A was placed below tape B. It was seen that tape A repels tape B in the positive y direction. It is known that the tape is positively charged because it is attracted to the negatively charged pen. Also, it is important to note that force equals mass time acceleration, and since the suspended tape is not moving, it is not accelerating, and therefore the net force in the y direction is 0. For this lab, the tape length was 0.2 meters, the distance between tape A and tape B was 0.021 meters, the mass of the tape was found to be 0.0002 kilograms, and the force due to gravity was found to be 0.001962 meters per second squared. In this lab, compared to in Lab 1, the tape will be modeled as a series of charges in a line rather than just as a single point particle. In the code, n equals 10, so the tape was divided up into 10 charges, as shown below. For this lab, the starter code is given and adapted using values I got during my experiment. First, the electric field is calculated. Next, the line charge function creates a line of n uniform point charges with a given total charge and mass arranged at equal intervals along a line segment. Then, each piece of charge in the top tape and bottom tape is iterated through. Electric field at the location of the piece of top tape due to the corresponding piece of bottom tape is calculated. And the electric force on the top tape due to the bottom tape is also calculated. Finally, the magnitude of electrical and gravitational force are returned. I first ran the code using the Q value I calculated in Lab 1, which is 9.805 times 10 to the negative 9th coulombs. As shown in the image above, the magnitude of electric force was much greater than the magnitude of the gravitational force. This does not support the fact that the top tape should have a net force of 0. So, a Q charge value of 2.3292 times 10 to the negative 8th coulombs is used. This value ensures that the gravitational force and the electrical force are equal and opposite, and result in a net force value in the y direction of 0. The magnitude of the charge on one piece of tape, as calculated by the computational model, is 2.3292 times 10 to the negative 8th coulombs. This value differs from the value found in Lab 1 because the charge is distributed along the length of the tape rather than just being treated as one point particle. In order to approximately determine the amount of charge on the floating tape, it must be assumed that each U-tape made had about the same amount of charge evenly distributed along the length of the tape, and that air resistance is ignored on the moving object. In conclusion, this lab shows that a better representation of a charge can be achieved by treating the system as a line of charges rather than just as a single point charge done in Lab 1. By distributing the charge evenly along the tape and then using a computational model such as the one shown in this lab, a more accurate value for the amount of excess charge can be achieved. This lab also shows that Python can be a valuable tool in order to calculate and model these interactions. Additionally, as was shown in Lab 1, this lab expands upon the topic of excess charge in ordinary objects and how their interactions can be easily seen in everyday life. Thank you for listening.